because there's a lot to talk about here. Yeah, but please feel free to ask questions in Zulip as I go. So guest debugging in Wasmtime. Here's what I'm going to talk about. I'm going to talk about what it means to debug at various levels of abstraction. I'm going to talk about what I built, which I've split into a bottom half and a top half. That'll make more sense as we go along. I'm going to give an actual demo of LODB attached via GDB stub to Wasmtime debugging code. And then I'm going to talk about future work. So what does it mean to debug WebAssembly? So you start, by writing some code in some language like Rust or C, and then you'll use a WASM toolchain to compile this into WASM modules, WASM components, and then you'll run this in some WASM VM like Wasmtime. And typically, if that's not an interpreter-based VM, that will do some compilation, either AOT or JIT, into compiled machine code. And so you have these three different levels of lowering at which your code is represented. And you could look at the code that's produced at each of those levels, right? At the source language level, it's, function main. At the WASM bytecode level, at least for typical compiled languages, that'll become a WASM level function. And at the compiled machine code level, you can look at the machine code that's actually produced. And you can imagine debugging at each of these levels, right? So you might want to single step through each of these abstraction levels. So if you debug the source language, you might want an experience that looks something like what you see in a host native debugger today, right? You set a breakpoint at the main function. You have source locations, main.rs line 10. You can print source level variables. So we'll call this source language level debugging. There are also use cases where you might want to debug the WASM bytecode, right? So I might want, and this is a pure hypothetical, sketch right now, a debugger where I can set breakpoints at WASM functions and see breakpoint locations in terms of bytecode offsets, and actually look at the WASM locals and globals. That would be pretty cool for certain categories of use cases. And maybe even disassemble the bytecode. So we'll call this bytecode level debugging. And then you might want, in other use cases, to be able to actually debug the machine code. And so this machine code in an environment like Wasmtime will be not just the Wasm functions compiled to machine code, but will be, calling into the Wasmtime runtime as well. And so sort of necessarily, if you're debugging at this level, you're going to see the calls, the transfers of control back and forth between both. And so we'll call this kind of debugging machine code level debugging. So who are each of these kinds of debugging useful for? So source language level, I would say, is most developers, most users of Wasmtime that we're targeting. This is the 95% use case, right? To them, the Wasm runtime or the Wasm platform is kind of irrelevant, like the kernel for native platform development. It's just where the code's running, but really you care about debugging your code. Debugging at the bytecode level and actually seeing, single stepping through individual WASM instructions would be pretty cool for people who are building WASM toolchains, right? So if you're writing a new compiler that targets WASM, this might be useful for debugging your compiler's output. Also performance-sensitive WASM developers, right? So you might want to see the WASM bytecode and what it's doing in the same way that performance-sensitive software engineers look at disassemblies of native code today. And then machine code level, right? So this is mostly just useful for Wasmtime developers, I would say, and there are dozens of us, uh, right? So that's a little bit glib. Like it's also maybe useful for people who are doing low-level performance work that depends on understanding what the runtime is doing as well. But there are a lot of downsides to that view as well. And so today we only support machine code debugging, I think because of some sort of like path-dependent reasons or economic reasons, I would say. It was pretty, expedient and easy just to allow attaching a native debugger to Wasmtime and emit enough metadata in order to allow that to see something about the Wasm. And it is useful, especially for us as runtime authors, right, to be able to see that, what the code is doing and debug it and how it interacts with the runtime. But it has a lot of downsides. So it's pretty flaky. There have been a stream of issues over the years with the bugs in our drawer translation, values optimized out. In general, providing perfect fidelity debugging with an optimized compiler is a really hard problem. And it's also confusing for someone who just cares about debugging their own code because you see a weird mix of the Wasmtime runtime with their own code running, right? So you single step into something that becomes a host call, and all of a sudden you're looking at Wasmtime's WASI implementation. And it's also, low level in the sense that it takes over the whole Wasmtime process. Maybe that's fine if you're targeting like the Wasmtime CLI itself. But if you have like an embedded, Wasmtime in some other context, maybe that's actually not possible or hard to do. And so We can do better, I think. And in fact, I've built a thing that I think is better for these use cases, for these audiences. And so the target here is source language or bytecode level debugging. And the way that we're going to do that is with what's called guest debugging, right? So this is a debugger built into Wasmtime itself that gives you a Wasmtime native view of the WASM VM as if it's an ISA that you can single step through, and then source language debugging on top of that. And so what do we actually want to build? So let's build, I'm going to introduce this terminology of bottom half and top half. The bottom half is what I call the piece in the runtime itself in Wasmtime that actually implements the APIs that allow, introspection, that allow single stepping, that allow breakpoints, all the things you'd expect in a debugger. And then the top half will be the UI or the interface on top of that. So for the bottom half, right, we want something that allows us to debug WASM on its own as if we had a native WASM CPU down to single stepping through bytecode. We want a fully WASM aware view of the world. So we want to be able to see all the WASM entities, right? If there are multiple memories, if there are GC objects, if there are WASM tables, exception objects, all of these things. And also built into the WASM engine itself so that it gives us a solid platform for things like record, replay, and reversible debugging, which I won't talk about today, but are on the roadmap for sure. Um, and so I'll break down sort of how we built this into and give a few details about the implementation in three different categories. So I'll talk about introspection. And so, that includes things like providing access to all the WASM entities, even the private ones. That one's kind of straightforward, so I won't say too much on that. But the more interesting part of introspection is actually giving a view of the current WASM execution state, right? So that stack, in every stack frame, the current PC, the locals, the operand values, the instance the stack frame came from, the function the stack frame came from, and all of that. And so that requires a lot of sort of insight into how the WASM bytecode is mapped into machine code. And then there's an API for breakpoints. So this involves actually somehow patching the code or getting control back at certain points in execution, which naively is hard if all you have is just compiled machine code. You have to somehow interrupt control and interject and get control back to the runtime. And then a debug event API, which is basically this infrastructure in the Wasmtime runtime itself to allow plugging in something else that gets essentially called from the WASM, morally called from the WASM, whenever certain kinds of events occur. So let's talk about introspection a little bit more, right? So this is a classic problem that every debugger has to solve. Somehow we need a mapping function, right? So you interrupt control flow, you interrupt control, you get a snapshot of the current machine state. We've compiled WASM down to native machine code. So we have the native machine registers, right here, the x86 registers, RIX, RBX, whatever, and we have a native stack frame. And somehow we need to compute what the view of the WASM VM state should be based on that native state. And it's somehow embedded in there kind of mostly, unless it was optimized away. But it's hard in general, right? And so the reasons this is hard is that values can be optimized out. Values may be moved around or rewritten through, typical optimizing compiler rewrites. And so, unless you build your compiler from the ground up to support this kind of like tracking of the injection, the mapping, WASM really loses its identity as the IR is transformed, right? It just becomes a soup of code that's mixed in with all of the other native code. And so there was a debugging RFC about 2 years ago now, spring 2024, that I'll call RFC V1. And the answer in that RFC was to use Winch, the baseline compiler, instead of CraneLift as a backend for Wasmtime for debugging. And the upside of this approach is that it has a well-defined and simple mapping from the machine state back to the WASM state, right? So it actually reifies all the WASM locals as slots on the stack. It reifies the WASM operand stack as the actual machine stack with pushes and pops, and so on and so forth. But it has a lot of other downsides with regard to feature parity, right? So it's mostly x86 only. Recently, they got to feature complete for Core WASM on AIR64. Doesn't have our other platforms, doesn't have Pulley, doesn't have RISC-V. And maybe even more importantly, doesn't have a lot of the more recent WASM 3.0 features like garbage collection or exceptions or stack switching or tail calls. So we could do all of that. We could bring Winch up to parity, and we probably should in fullness of time. But I started to think when I looked at this landscape that maybe I didn't want to put this on the critical path of getting good guest debugging. And so we can ask the question, how can we reuse all of the work that went into the CraneLift-based backend and build something on top of CraneLift instead? And so the answer I came to is actually kind of this deceptively simple idea. It took a lot of thinking and then realizing, oh, wait, no, we can just do this. And so the idea is let's emit IR to store the values as part of our state, right? So let's look at how some WASM bytecode gets compiled. We'll have, getting a local, and then we'll add zero to it, right? So an optimizing compiler should see this and say, oh, you're returning x plus zero, we can just return x. Right, so crane left indeed will rewrite this cliff, this IR that I'm showing on the right, to not have the add and the constant zero, just return the original value. So you can imagine now if we're single stepping through the WASM bytecode and we stop like after the const is zero, what's the top of stack, right? We've optimized that away, so we don't actually have part of our WASM VM state anymore. And larger and more complicated versions of this are exactly why you see in debuggers debugging, optimized code, the value optimized out, right? You see that classically in like GDB or LODB. Um, and so the insight with instrumentation-based introspection is that we can just not do that. And so basically what we do instead is we define a new stack slot in the native stack frame for every compiled function, and we insert code that actually updates the memory state in that stack slot, corresponding to the WASM VM. Right. So after every, let's say, stack pushing operation that we compile, we'll generate IR that does an IR level store into that state. And likewise for locals and likewise for any WASM VM level state, right? So we sort of turned the problem on its head and said, instead of trying to reverse engineer the output of the compiler and figure out, where something that has disappeared is computed, we say we're just going to compute exactly the output that you want, which is the view of the WASM VM. And so the compiler can do whatever it wants to optimize. This is fully robust against any, crane lift pass we could conceivably build because stores are robust side effects that, must not be changed. That's a compiler correctness invariant. We preserve the state by making an explicit output. There is some detail I'm not showing here regarding sequence points. This does have an overhead. We're inserting a whole bunch of stores to stack frames. That overhead I've measured at about 2x, which is a big hit, but actually that's still better than the 4x that you take by moving to winch instead of crane lift. Um, and so we get perfect fidelity in the WASM VM state. So the next thing is this event infrastructure, right? So we basically want to have a facility for registering a handler to be invoked on various events. And I won't go into too much detail about exactly how this interacts with the async stuff in Wasmtime, other than to say you basically register what looks like an async host call, and it gets this debug event. We can add to this enum over time. Right now, it gives you events on things like traps, breakpoints, epoch yields, host call errors, and exception throws. But we could certainly add more, memory watch points in fullness of time. There were a few key design choices that we hit when we were thinking about how to do this. Um, so we sort of made certain choices here to make things a little bit simpler. And so one choice is how do we actually ensure that the store in Wasmtime is frozen when the debugger has control, right? So what we want is this sort of control flow where guest code is running and then we hit a breakpoint or some other debug event, and we want to basically have this coroutine like ping pong between the debugger and the debuggy, right? So we freeze the debuggy and we transfer control to the debugger. And then when the debugger says run, then we let the debuggy continue. And so the way we do this is basically saying that it looks like a host call, and the host call gets a store context mute. So at any point in the WASM, when we hit a debuggable event that has, and there's a debug event handler registered, we essentially do the equivalent of a host call and pass in mute borrow of the store. And because of Rust's, borrowing rules, that means that nothing else can run in the store. So there is some async component model stuff that should eventually be done here, making this work with the accessor paradigm that Alex and Joel have built. That doesn't, we don't do that yet. And so what this means is we just freeze the entire store when the debugger is active. And then the other thing that we sort of went back and forth on is whether we actually do host calls or whether we do something smarter with, say, signals, right? So you can imagine keeping the compiled code that we normally have that uses signals to inject like traps. Right, so you hit a divide by zero in x86, that gives you a sig FPE. You hit an out of bounds if you're doing virtual memory base bounds check, that gives you a sig segv. And maybe we want to somehow intercept that signal and give the debugger hook in Wasmtime control from the signal handler, maybe indirectly. And so the way I actually did prototype this, and the way that this worked is what I called call injection. So in the signal handler, we would actually push a new stack frame. We would mutate the state of the thread that was interrupted. We would push a new stack frame under the WASM stack frame that looks as if the WASM did a host call into the debugger. And so this basically kind of almost pretty much worked in Linux. I wrote the assembly for all four of our architectures. Um,
I'm good
but
on it.
it is
Cool.
So you
really,
saw the money I moved this
Yeah.
morning? That was
So I
quick.
just
That was
need to-
good.
Yeah.
sorry, could
I
you
needed
mute
that
David?
Because Daniel's
David, could you mute? Thanks. So it pretty much almost worked, but it's very brittle in the sense that, or not portable, I should say, in the sense that every OS is a little bit different. So Linux gives you the ability to mutate the stack. Windows doesn't because there's no red zone there. Mac OS, you run in a different thread. So you have, anyway, so there are different things you have to do on every platform, a whole bunch of like fiddly assembly. And then sort of the other thing that really killed this is that dealing with point of provenance and store ownership when you don't have an explicit host call that actually passes in a mute reborrow of the store, is kind of a tough nut to crack. And so basically, we went back on that and we said, let's do actual host calls. So fortunately, in Wasmtime, thanks to Alex's work like a year or 2 years ago, we have the ability to say we don't do signals-based traps, we do instrumentation-based traps. And so we pretty much just use that. The one thing that's a little bit interesting is breakpoints. So let's talk about breakpoints now. So really, we don't want this world where we like have a dynamic branch at every possible breakpoint, which is, between every WASM bytecode instruction. And so native debuggers do something that pushes the overhead to the away from the common runtime case and to the breakpoint insertion case by actually editing code, right? So the way that like GDB will insert a breakpoint in a Linux process is that it will actually edit the .text and it will insert an instruction that delivers a signal like UD2 on x86 at the point where the breakpoint is. Um, and so maybe that's what we want to do, right? So there are a few design axes that we considered here, and one of them is: do we edit the code? Do we do this thing where we insert new code, which is slow to update, complex, but has low runtime overhead because in the common case there's no dynamic branch there, or do we do the dynamic branch? And then the other design axis is actual call or trapping instruction leading to signal-based call injection. So we kept it simple. I already said basically we gave up on the signal-based call injection, so we want an actual call but we can still do an edit-based thing and insert the call dynamically. And so that's what we did. So I added functionality to CraneLift to have what we call patchable calls. And the way this works is that we put a no-ops just big enough for a call instruction. So 5 bytes on x86, 4 bytes on the risks. That is NOPS by default. But we have functionality now to actually edit that and insert a call to what we call the breakpoint trampoline. And this trampoline has a custom API, so it doesn't clobber any registers, right? So it doesn't affect the compiled code. It really is just NOPS inserted at certain points. So this trampoline will save all the registers, and then we'll actually do a real host call. So we reuse all of our host call infrastructure for that. And then we insert all these patchable call sites, and we emit metadata during compilation saying for this breakpoint at this WASM PC in this module, patch this offset this size in the CWASM with these bytes, which is a call instruction. This required some new infrastructure in CraneLift to distinguish between the shared module code, which we now call engine code, and private copies of the code, which we now call store code for every store. And then, yeah, dynamic patching, so unpublish, edit, republish, iCache coherence, all of that fun stuff, all that's handled now. And so now we have the ability to actually turn on breakpoints by patching and call instructions to a host call. And so then single stepping is the other thing you want in the breakpoint universe. And you could do something complicated. I opted not to, and it's good enough. And so the not complicated thing is single step means enable every breakpoint in the module. Yeah, so that's what we do, and it's good enough. So the final thing I'll talk about in implementation detail here is stack frames, right? So you want to be able to walk the WASM stack when the store is paused, the debuggy is paused, and look at all of the debug state slots that the instrumentation inserted, as well as the VM context, as well as the WASM PCs, etc. And so the initial idea with my Rust brain on, right, I said, let's build a safe iterator that actually takes a mute borrow of the store, holds that borrow of the store, and then lets you walk the stack frames while the store is borrowed. And so that's fully memory safe, right? So the thing you want to avoid here is basically having raw pointers into the stack flying around that could be invalidated, if the debugger tries to look at them after you have the WASM continue and unwind that stack. Um, but it turns out that debuggers actually do want A, to hold multiple stack frame handles at once, and B, to do other things with the store while the store is frozen. And so this like iterator, external iterator that holds a borrow of the store thing turned out to be a little too limiting when I got to actually building the top half. And so I asked, okay, is there a way that I could actually have like an entity handle in the same way that we have entity handles for instances, for tables, for memories that refers to a WASM frame, and then somehow intelligently deals with the case where the WASM continues and that frame is no longer valid. And so the idea that I came on is this thing that I'm calling versioning, execution versioning. So it turns out that it's sufficient to say we have one counter, the version counter, which is just a U64 in the store. And every time you return into WASM, you increment that counter. Now, if you hand out a frame handle that is a raw pointer to the stack, like the actual machine stack, but you stamp it, you mint it with the store ID and that execution version. And before using it, you always check that the store is still at that version. That is sufficient to implement lazy invalidation, right? So what that means is that as soon as execution continues, that it can only continue by returning into WASM. You might think, okay, but what about dropping futures? That actually returns into WASM and unwinds as well. And so this is sufficient to give us a fully memory safe thing that can have a whole bunch of raw handles under the covers. To use them, you pass in a mute borrow of the store at the time that you use them, so it still respects the rest ownership framing that we have. And so this gives us the ability to basically cache handles at every level of the stack. Um, okay, so that's the bottom half. Let's talk about the top half. So the vision in the RFC-v1 was this thing called debug adapter components, right? And so the way that this was framed was we could just fall into the dwarf monoculture and say that let's just, implement like a debugger that understands dwarf and the WASM modules, and that's the end of it. But maybe there are other languages. Some are compiled, some are interpreted, some will be new compilers that can design their own debug format. Let's actually try to foster an ecosystem where you can build an adapter for whatever debug format you have and sort of ship it with your language. And then Wasmtime could understand, okay, this component has this adapter, that component has that adapter. And then Wasmtime would basically have a multiplexer at the very top that serves something like DAP, the debug adapter protocol, which is a UI level view, right? So it's a very high level view that talks directly about frame variables and evaluates expressions by just passing the string, which is the expression. So it expects all of the smarts to be in the debug adapter. And Wasmtime will multiplex into these different adapters. I looked at this when I got to the point of building the top half and realized debuggers are a lot of work. This is hard. And that's fine. Maybe that's the job we signed up for. There's the question of could we do something maybe that's a little bit easier in the meantime? Just to give a view of what this would take for, classical C, C++ Rust debugging, basically, what this would mean is we would need to either take LODB or build the equivalent of LODB, including things like the C++ expression parser, type system understanding, arbitrary expression evaluator, which does JIT, by the way, pretty printer ecosystem, which involves a whole library, Rust, the standard library ships with pretty printers for like VEC and HashMap that uses Python. So by the way, we would need to embed a Python interpreter in the thing. And so this is just like a whole bunch to basically, probably borrow from LODB and take apart and rebuild, but that's a lot of refactoring. And so we want something in the meantime. And so in the meantime, actually, while we were sort of thinking about all this, LODB and V8 and JSC, their respective WASM engines, evolved a WASM-specific extension of the GDB stub protocol. So GDB stub, for those who don't know it, is this ancient thing come straight from the 1980s where you have an embedded system with a serial port and you connect your host system to that serial port, and GDB can basically control execution and do debugging, introspects the stack, introspect locals over that connection. And so it survives into the modern time. This is the way that you can attach GDB to, say, like QEMU. There are a whole bunch of GDB stub hosts that are implemented. And it's actually not terrible with this WASM extension. It supports multiple modules, it supports multiple memories. It has this basically synthesized address space that has all of them, in this one address space. And it works, and it's kind of the direction that things are going, at least for dwarf based languages. And so maybe we want to just plug into that ecosystem and take advantage of that. And so I sort of went then far in the other direction and said, let's just build native GDB stub as part of Wasmtime using this bottom half set of APIs. The compromise that eventually I came to when talking through sort of ecosystem implications of that is that we don't want to completely hard code GDB stub and cut off the flexibility where, someone else might still want to build their own debug format later. Instead, let's do this thing where we still have the bottom half APIs in a WIT world for a debug component to use, but let's give it the WASI CLI world on top. And we call this debug main. And so this gives you a lot of flexibility. This means that you could implement, a full dwarf parser and serve DAP and all of this over, WASI sockets, TCP sockets, or WASI HTTP or whatever. You could implement GDB stub and serve it via a socket. You could implement, a text mode curses interface. You could do an equivalent of like the old MS-DOS debug.com and a machine monitor. You could do anything with this, right? The possibilities are endless. And so this basically is what we decided on. By the way, we as a project haven't technically decided on it. The RFC is open. I posted it 4 days ago. Please go approve it if you agree, or discuss otherwise. But this is sort of the plan of record tentatively. And so that is what I built. I built the WIT world, and I built a GDB stub implementation that lives in this world. So I'm now going to Command Tab over to my terminal, and I'm going to show you this running. So here I have, oh yeah, so it's not perfect yet. So here I have a Wasmtime. This is in my own branch. All of the changes that I've made to core Wasmtime, the Wasmtime crate, by the way, are already upstreamed. Thank you, Alex, mostly for all the reviews. The WIT world is not yet, but I will do that as soon as the RFC is approved. I have this -d debugger, and I'm pulling in the GDB stub component, which is indeed a WASM component. And I can show you the world, debugger, debuggy. It has a bunch of stuff, single step, resumption, read and write memories, WASM exceptions. From a frame, I can get the locals, I can get the stack. We have WASM values. So we can do everything we need to do as a debugger with this API. And I'm giving it an arg. So this is the WASI CLI part. You can give it argv. Let's serve GDB stub on port 1234 of localhost. And we'll run test.wasm. What is test.wasm? Uh, uh, what is test.c, I should say? It's a little thing that computes the Fibonacci sequence. Okay, so let's run that. I've enabled the debug printing in my thing just so you can see, more interesting stuff. See the matrix go by. You need LDB that has the WASM target built in. It turns out that Debian's default LDB doesn't. So maybe we could ship this as part of WASI SDK eventually. And we're going to connect to the process, and we're going to break on main, and we're going to continue. And we see that we're now in main. If I switch back to the Wasmtime thing here, you see it's speaking this protocol. That Q WASM call stack is query the WASM call stack. So this is using the WASM extensions to GDB stub. I can break in fib. I can continue. We're in fib now. Next, PA, PB. I can view locals, psum, and finish. Okay, so that actually is an LDB bug where LDB will die once the command finishes. So that's sort of an interesting thing that I'll need to debug in LDB. But if I connect again, next, bmain, continue, next, then yeah, we should see the result. So printed result, and then we see a bunch of queries. So basically, this is working. It's a little bit flaky. In the sense that LDB's support still seems a little bit weird. So again, if I continue, LDB crashes. But yeah, it basically is there. So what's the future work? So after the RC is approved, please go approve the RC. I will land all of the rest of this work. And then there's record replay, reversible debugging, which I didn't at all talk about today, but that's sort of, continuing work after this. Maybe eventually we'll get to the debug adapter vision, given sufficient resourcing. That is, I think, probably like an engineer year of work to build out. I don't know if I can afford that in my own personal timeline roadmap, but that is something we can talk about. And then there's a discussion question, which is what do we do about our existing host debugging? It's still there. Maybe in the fullness of time, if this covers everything that we need for WASM, we don't need the other dwarf transform anymore. Please discuss. Yeah, that's basically all I had. So in the 2.5 minutes left, I am happy to answer questions.
Yeah, I don't know about you all, but my heart is absolutely racing after that demo. Yeah, so you have a number of folks in the chat who are just very supportive and excited. There's a question from Mindy. Would this debug WIT interface be Wasmtime specific?
It doesn't have to be. We could go through a standards process. If you squint enough, looks like a reflection API, and including things like it could have things like dynamically spawning an instance or a component. And I know there's been discussion about that in the component model as well. So I haven't thought too deeply about that. I kind of just wanted to sprint and make this work for Wasmtime. But that is an interesting sort of follow-up. Yeah.
Any other questions from folks? I'm waiting for someone to say, when can I use this?
As soon as I land it, please approve the RFC.
I guess I have a quick question. If well, first of all, I love the idea of implementing debug adapters using components. I think that's awesome. Are there any drawbacks to doing that?
Um, Yeah, well, so drawbacks versus what, I guess is my question. Drawbacks versus a native hard-coded top half that's in the CLI or uh versus what?
Yeah, I guess the alternative would be like some sort of WAS host level Wasmtime plugin, I suppose, to allow multiple implementations, possibly not maintained within Wasmtime. But yeah, I guess
Yeah.
that maybe such a route would allow host magic that we might, but I can't think of anything, and that's why I'm asking, I
Yeah,
suppose.
I mean I think to the extent that one needs additional APIs from Wasmtime, we could add them to this world. And so then I guess my thought on that is we're talking about plugins into Wasmtime. Wouldn't it be cool if we had a technology to allow plugins into a program? And we do. It's called Wasm. And so I think basically uh, this is nice in the sense that you can develop without building the thing into Wasmtime itself. I can speak just personally as I was developing this GDB stub implementation. It was super nice to have like half-second rebuilds on the Wasm component rather than rebuilding Wasmtime. And there are all the safety aspects as well. So whatever. I think that if we hit any use case where we can't build something today because we need some additional capability, we should just add it to the API. That would be the answer. Yeah.
All right, we're already out of time. I will allow two very quick questions, so very brief. Nick, you first.
Uh, yeah, I just wanted to say super fantastic to see the demo come together, and I'm really excited.
Thanks.
And Alex.
I would echo that. Are the LDB stuff, is that all upstream or is that like extra patches for
Yes.
LDB?
So I checked out LEDB Get and built it, and that's what I was running.
Nice.
Yeah. So the only caveat is that, again, I think most distros that just build and ship LEDB, like Debian's package or whatever, don't include the process WASM support. And so I think we probably should include in WASI SDK the build of LEDB, but
I
that
agree.
shouldn't be hard.
And there are more questions that are in the Zulip. Folks are very excited. Please continue any additional questions you have. Just throw them in the Zulip, and folks are more than happy to get back to you on them.